Now we're ready to go and look at some more probability studies. And we'll start out with Section 3, the general rule for a union of two probabilities. So if I have a Venn diagram like so, and if I want to find the probability of A happening or B, that actually means that A could happen or B could happen, or actually both of them could happen. So this doesn't mean that if A happens that B doesn't. It could be if I have A or B happening, one or the other or both of them could happen at the same time. So in our picture, we would want all the stuff that I have shaded in here to be counted in the union of these two events. So notice what would happen if I find the probability of A, and if I add to it the probability of B, I would have double counted all of this information that was in this double hashed area, and that's actually the intersection of the probability of A and B. So if we have two events who are disjoint events, as in the case in the other page that we are just looking at, if our events looked like this, where our A and B did not intersect, we can simply find the probability of A, the probability of B, and just add the two together, because in this case they don't have an intersection. However, if the two events can happen at the same time, we're going to have to be careful about double counting the intersection. We will have to subtract it away. Now, another term that we worked with in FS was conditional probability. And remember, conditional probability is written in this type of notation. We also call this little mark here given. So I'd say the probability of B given that A has occurred. And pictorially, that means this. If I look up at my Venn diagram again, we know that the given condition has taken place. So we know that A has taken place, and we're trying to find the likelihood that B happens given that we know A already took place. So in order to find this probability, what we do is we actually take as our denominator the probability of A. And we find what part of A, this little double hashed region, is A. So we find the probability of this intersection divided by the probability of the whole. And that gives us the probability of B given A. Now, in general, if we want to find the probability of the intersection between two events, if there's something that's countable, that we can just count the intersection, like for instance, let's say I gave you these numbers. I'm going to give the numbers 1 through 10. I'm going to put them in set A and or set B or both. Let's say I have the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so I have 10 numbers. And we know set A is the set of 1, 2, 3, 4. Set B is a set of 3, 4, 5, 6, 7. And so if I asked you what's the probability of having A and B happen at the same time, we would literally just count. There are two ways for that to happen out of 10 whole numbers in the sample space, and so we'd say it's 1/5 or 20%. We don't take and just multiply the probability of two events together to find the intersection. And again, if we can see the Venn diagram or see the whole sample space and count how many are in the intersection, that's the easiest way to do it. But in general, if we want to use a multiplication rule, if we want to find the probability of A and B, we find the probability of the first event happening, and then we multiply it by the conditional probability of B happening, given that we know A already took place. Now that can also be written this way. If it's possible for A and B's order to be switched around, we could also say find the probability of B and then multiply that by the probability that A takes place, given that you know B already took place. And if you'll notice, if I take this equation and if I divided both sides by the probability of A, I would end up having this conditional probability statement. So these two are totally related together. So let's look at the next question. So So we have call a household prosperous if its income exceeds 100,000, and we're going to call that event A. And call a household educated if the household has completed a householder, so someone in the household has completed 4 years of college. And let's say we're going to again look at census data, and census data tells us that the likelihood that A happens from census data several years ago was 12.5%, and the likelihood of the educated taking place was about 23.7. Also, the joint probability, which means the intersection of the two, occurs 7.7% of the time. And so I want to know what is the probability of A or B happening. Now, once again, as I said before, that doesn't mean that they can't happen at the same time. You just know either A happened or B happened or possibly both. I drew a little Venn diagram in B. Let's look at that first before we look at the answer over here at A. And in my Venn diagram, here's A, here's event B. And the one common mistake that people will make is the intersection we know is this 0.077, so that naturally goes here in this little intersect region. But what quite often people will do is they'll take the probability of A and put all of the 0.125 in here. We need the sum of these two to be 0.125, just like we need the sum of these two to be the probability of B, so be careful about that. So now notice, when I find the probability of A or B, I can follow the general rule for the union of two. I can find the probability of A, find the probability of B, and then subtract away the intersection. I could also look at my Venn diagram and just add these little three components together to get this same probability. Now next I want to find a couple of conditional probabilities, and we can look at it via formula. If we have probability of A given B, we find the probability of their intersection divided by the probability of the conditional. To find the probability of B given A, we again find the probability of the intersection divided by the probability of the given conditional. Now, I want to look back at the picture because the picture really makes these formulas make sense. In this first one in C, you know B took place. So if I come up here to this Venn diagram again, I know B took place. I'm really trying to find what part of B is A. So I would say, well, I have 0.077 out of that whole. 0.077 out of the whole. On the other hand, when I look at the conditional probability here, I know A took place, so I have this circle. And I'm trying to find what is the likelihood that B happens, given that I know A took place. So I take this part out of the whole, or the 0.077, out of the whole probability of A, which is this 0.125. So hopefully if you think of a picture, you can think of where this formula comes from. It's great to know the formula, but it's really better to understand what the concept is that we're trying to cover. Now, if I want to look at are A and B independent, remember I can do this little test. I can figure out what the probability would be if I multiply these two together. If the two events are independent, the probability of A times the probability of B should be the same as the intersection probability. Now, when we multiply these together, we find out we get about 3%. In reality, the intersection is 0.077 from the given information about the joint probability. So these definitely are not independent events. If they were independent, they would only occur together about 3% of the time. They occur together over 3 times that. They occur together 7.7% of the time. Now, the last thing I want to look back at is the tree diagram that is example 2. And in the tree diagram, we have the information that only 5% of male high school sport players go on to play sports at the college level. So I'm going to start my tree. 5%, and I'm letting A stand for competing in college. And I know 5% will compete in college, 95%, the complement of that is they don't compete in college. Going back up, of these who compete in college level, only 1.7% enter major league sports, professional sport of some kind. So if you've attended college, then we have 0.017 will actually go on to play professionally in the major leagues. Now, this branch of this tree is actually a conditional probability. Oftentimes, we won't write that conditional part down, but this literally is a conditional probability on the second branch. This is not conditional, nor is this conditional. But every single branch beyond the first is a conditional probability. So I like to write it as so I can answer questions more clearly in the end and have it labeled a little more clearly. So if you have competed in college, you have a 1.7% chance of playing at the major league. Therefore, you have a 98.3% chance of not being in the major league. Now let's continue on with the information. The likelihood that a high school player goes to a professional team is only 0.01%. So if you are this route where you're not competing in college, it's very unlikely that you're actually going to be playing at the major leagues, like a LeBron James. So you didn't go to college and compete in sports. However, you are competing at the professional level, which means you didn't play in college sports and you didn't professionally play ball. Most people are on this part of the tree. Now we have one more piece of information. We know that 40% of athletes who compete in college and then go to the pros have a career that is more than 3 years. So on this branch, those who go to college, play professionally, we know that 40% of these, and this really should be 40% of these people actually go on and have a professional career that's more than 3 years, which means 60% of the people don't have a career that's more than 3 years. It lasts 3 years or less. So there's our tree. Now, we don't know the information about these. We can't infer anything about what happens to these branches afterwards. So we don't know what the longevity is for someone who didn't play in college but plays professionally. We don't know anything about the length of a career. So let's use our tree to help us answer the questions below. I want to find the probability that someone not only competes in college, but the person also competes professionally. And to find that probability, I literally multiply again these two values together. I find the probability of A times the probability of B given A. And remember, this answer is not the probability of B. I don't actually know the probability of B. We're going to find that below. Now I want to find the probability that someone competes in college, plays professionally, and has a career that lasts more than 3 years. Well, that's along this branch of the tree. 0.05 times 0.17 times 0.14 by 0.4. Doesn't look so good. Now lastly, I want to find the probability of B. Before I said we don't know that probability. We weren't given that. So B is the probability that someone plays professional ball. So if I look up here, there are two ways to play professional ball. You can go to college and play ball, or you can not go to college and play ball. And so here is the part of playing in college and playing ball, or not playing in college and playing professionally. And so the sum of these two gives me the probability of B. Now finally, I want to find the probability of, given that someone does play professionally, what would be his chance or her chance, most likely it said male, so his chance of having played in college. So again, given that someone plays professionally, what's the chance that you randomly pick a person who plays professionally? What's the chance that that person actually competed at the college level? So I find the probability of the intersection, divided by the probability of the conditional. And I find out that that's about a 90% chance. And I think you are ready to practice.